We're going to finish up section 2 today. How would you read that? What does it mean? What does it tell us? That's it? No.
Is it
Anybody?
the limit of f of x is equal to L as x approaches the constant?
Yeah. Well, yes. That's as x, because this is the important part. The limit of the function f of x is L as x approaches c. That's what we're gonna spend the whole first chapter about, is talking about this concept. So what that means is, as we talked about last time, here's our function. So in this example, I think it was that, so like that. Now, what this thing's telling us, and we're going to expand on this in the next section, but here's our function. The c value that you're looking at is typically the x value where troubles occur. The function's undefined, the function blows up, or something like this. What happens in this case? What happens at 1? If we plug in 1 to our function, what happens? We get 0 over 0. And we talk about it's either undefined, it's either 1 or it's 0, because it follows all of those. 0 over 0. It could be 0, it could be 1, or it could be undefined. Because think about it, it goes through all three of those rules. Anytime you have a 0 on top of a fraction, what does that mean? It equals 0. Anytime you have the same number top and bottom, it equals 1. Anytime you have a 0 on the bottom, it's undefined. Yes. In this one?
0 over 0.
No, the rule is this, is any number over itself is what? Is 1. That's the concept, that's the rule you have to go by. What did you say about equals 2?
Yeah, because 0 is special where you multiply anything by
No, it's not 0 multiplied. This is what the end result. When we plug in 1, in this equation, what do we get? We get 0, 0. We're not plugging in 0. We're plugging in 1. This is our c value.
No.
But yeah, this is the result, not the operation. So whenever you end up with this, but actually, whenever you have 0 over 0, that is a blessing in disguise. As this one told us, is whenever you have that, that means it can be simplified. There's something we can do to make it a lot easier. Now, the value 2 in this equation, what's f of x? Out of this example, what's f of x? The function itself. What's L? But what in this example, what is the L? No. 2. This is your L. X is all the x values you have. Those are your x values. The c value is what happens, where's the point where the trouble occurs? That's how you define these things. Now, we know that in this case, the limit of x squared minus 1 over x minus 1 as x approaches 1, this case, it equals 2. Why does it equal 2? Well, the way we figured out last time was we took this equation on the top. We could factor out the numerator. Because we had 0 over 0, that means there's something in common in the numerator and denominator. In this case, it's the x minus 1s. So this equation comes down to being x plus 1. So now when I plug in 1 in place of x, what do I get? 2, which is my limit. Which is also a hole in this case because of the value I had to remove from the simplification. Right? So what this is telling us now is what we're looking for a limit. A limit is not necessarily an exact value, it's where the function approaches. The limit is at what value does the function approach as we get closer to some value c. And then we'll also talk about the properties that have to exist for this to be true. I mean, we talked about it earlier last time. What functions do we know automatically that this doesn't work on? Remember this example? What kind of function is this? What do you call this kind of function?
Piecewise?
You could say it's piecewise, yes, but it's got another step. It's got a jump discontinuity. But yes, I can see you can define this as a piecewise, yes. But yeah, in this case, you have a jump discontinuity. Another one that we saw was when it oscillates violently between +1 and -1. If the function oscillates, we have a jump discontinuity. So continuity is a very important concept here. Continuity is very, very, very important here. As we'll talk about in a lot of our examples, all the theorems we talk about, we're going to start off, we're going to preface by saying, let f be a continuous function bounded on this interval, or let f be a continuous function in this open interval. So continuity is a very important concept. Now, where did I leave off last time? We left off. Oh, well, let's start with this. We're going to talk about the properties of limits. Theorem 1. Okay, what is a theorem? Anybody ever heard that word before? Let's pretend this. Ever heard of Pythagorean? Pythagorean what? Pythagorean theorem. Yes, you guys have ever since junior high, elementary school, you've done a Pythagorean theorem. A theorem is just short of a law, in which it's always, always, always true. It's just that we have not found a counter positive for it. So a theorem is a idea that is very well structured, but we have not found a reason that it does where it fails. When we deal with theorems, every section we're going to deal with, every chapter, the theorems are going to define the what, when, where, and how of everything we're going to talk about. So if you ever get stuck in a homework problem, read the theorem and see how it connects to the problem that you're trying to solve. This is where you get all your answers from. Okay, theorem 1. Let L, M, C, and K be real numbers. And the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is m. What we're doing here, we're laying down the groundwork because now comes the properties. Then if those are true, then we have the sum rule. The sum rule says this: the limit as x approaches c of our functions, the sum of our functions, f of x, g of x, is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x, which, as defined above, equals L plus M. So what does that theorem tell us? What does that first one tell us? Well, if we have the sum of an equation that has two terms that are added together, we can split them up and do them individually. The second one should have been with that first one. It's called the difference rule. And it deals with the limit as x approaches c of f of x minus g of x I could split those, I could distribute, not really distribute, but I could separate them into two separate functions. The limit as x approaches c of f of x minus the limit as x approaches c of g of x, which becomes L minus M. And the worst thing is, anytime we have a theorem that these properties, you're going to see these over and over and over in all different types of configurations. So the sum and difference rules pretty much saying the same thing. If you have an equation that has multiple terms separated by a plus or minus, you could just do them independently. All right. The next one is the constant multiple rule. What this one says is if I have the limit as x approaches c of some number times my function, because the constant term itself is not a function of X, I could bring it out in front. Which now means my final answer is K times L. Because the limit of f of X is L. The next one is the product rule. What does product mean? Multiplication. So this is saying is the limit as X approaches C of f of X times G of X I can split those up as limit of f of X times the limit of G of X as X approaches C, which then becomes the product of the limits. The opposite of product is the quotient. Quotient means what? Fraction. So we have the limit as X approaches C of f of X over G of X which means we're taking the limit of each function separately. Limit of f of X over limit of G of X is equal to the limit of L over the limit of N. As long as G of X does not equal 0 and M does not equal 0. There's always a exception to the rule unless the numerator is also 0 at that point. Remember, it's just that individually, you cannot have G of X equals 0 or M equals 0 unless the top is 0 also. The power rule. This one tells us as we take the limit as X approaches C of some function raised to a power, what this is not really true, but what it really means is now we could separate these. This exponent occurs outside the limit itself. So what it really looks like is this. Which becomes L to the power N. the root rule. Let me write down first and I'll show you. These two, 6 and 7, are the same thing. The limit as x approaches c of the nth root of f of x How are roots and powers related? How are radicals and powers related?
They're inverses of each other?
No, that's what I said, no. You can say that, but they're not related that way. The way they're related is this way. And if you have a radical to the nth, this is your root. That can be written algebraically as a rational exponent. So in other words, we can take the root theorem, the root rule, we can rewrite it as a radical root or exponent. So you see, now we have the same rule. So according to this, the limit of f of n is L to the power 1 over n. What that can be written out again is the radical of L. And we can take it one step further by combining these two rules. If you had the nth root of f(x) to a power m, this can be rewritten as we could be like this, which could be taken back down to. So that's how they're related, as radicals are actually exponential equations. All right, let's look at some examples. So we have we have the limit as x approaches c of x cubed plus 4x squared minus 3. We're going to look at this one just really quick, and then I'll show you the shortcuts for it. Actually, the shortcut is what you would normally do here. Anywhere you see an X, put a C. But let's follow the properties. Because we have 3 separate terms here, we have addition here and subtraction here, we can use the first 2 properties. We can split these up. So we have limit of x cubed plus the limit of 4x squared minus the limit of 3. That's using the limit properties 1 and 2. What did it tell us? Yeah. Now, do we have any other properties we can use here? We have a constant multiple. What does that one tell us we can do? This is a constant multiple. It can go out in front. And then 3.
What do you mean that it will be constant multiple?
Well, the limit looking for is as x approaches c. As x approaches c, does 4 change value? No, it's always going to stay 4. So it doesn't serve any purpose of it. So we put it out in front. So now we're worried about as x approaches c for this equation.
So 3 would be a constant had an x in it?
What's that?
3 would be a constant if it had an x in it, right?
In this one?
Yeah.
Well, 3 is a constant. It's not a constant multiple, it's a constant. So no matter what value x you put in there, what's the limit going to be? It's going to be always 3. So there's that property. It says the limit as x approaches c of a constant is equal to that constant itself.
Okay.
So that's the basic property we talked about last time, actually. We actually the 2 basic properties, and the limit as x approaches c of x is c. And these are the 2 rules we're going to live by. So in the first one, what property do we use here? The power rule. So as x approaches c, what we have here is the limit of x as x approaches c cubed plus 4 times the limit as x approaches c of x, all that squared, minus the limit as x approaches c of 3. And we are taking the long about way of doing this step by step so you see what's happening.
So do you put the 4 outside the bracket always?
But it's constant again. It doesn't it contributes nothing as x approaches c. Because no matter what x is, we'll multiply by 4.
Yeah.
So we can move it out in front and then do what we're gonna do with x and then multiply by 4.
So what matters first is the exponent.
Well, the exponent, by order of operations, the exponent is more important. It's changing the value itself because it's no matter what x is, I have to square it. So we have to do that first, and whatever we get there, then we multiply by 4. Good questions. So can we do anything else in here? No. Now we use this property, the basic properties. So the limit of x as x approaches c is c to the power 3. For limit of x as x approaches c is becomes c squared minus the limit of 3 is 3. So there's your answer.
You go to, you go, yeah.
Remember, I'm gonna send you all this stuff anyway, so there's to keep us moving forward. Let's look at B. The limit as x approaches c of x to the fourth plus x squared minus 1 over x squared plus 5. Since the quotient, basically what it's telling us is I could take the limit of the top and the bottom separately. And similar to as we just did above there, basically what you do now is anywhere you see an X, put a C. So we have C to the fourth plus C squared minus 1, C squared plus 5. And there's your answer. And the last one, limit of the square root of 4x squared minus 3 as x approaches -2. So the first thing you actually want to try anytime this happens, just plug it in there, see what happens. So anywhere I see an X, I'm going to go straight to -2. So by the order of operations, -2 squared is 4. Four times 4 is 16. 16 minus 3 is the square root of 13. And there's your answer. If it gives you an answer, what if it gave me 0? If this gave me 0, what would that mean? What's that? You're wrong.
Possible outcome?
No.
Possible.
No. I know what you guys are thinking about, but what conditions did those earlier answers give us? Where did those come from? What kind of equation was it? It was rational. We had 0 over 0. If this became 0, 0 is an answer. Is 0 a possible answer? Yes. It can cross through the origin. It's just if the final answer is undefined or if it violates some rules. In other words, if we had -13, then we'd have issues. But the answers could just be that simple. That's why the first thing you want to do if it gives you a number, plug it in there, see if it works. If it doesn't, if it gives you 0 over 0, or if it gives you some sort of square root of a negative number, then see if we can fix it algebraically. But remember this, that's undefined may be a solution. If we exhaust everything possible, what we're left with is an undefined answer, it may be no solution. Like Sherlock Holmes said, after you remove all the possibilities, whatever's left, however improbable, is the answer. Oh, theorem 2. Polynomials limits of polynomials. Actually, theorem 2 and 3. It sounds like it's going to be impressive, but here's what it's saying. If your polynomial P of X is equal to A X N, no, I'm making A sub N, A N minus 1 X N minus 1, A N minus 2 X to the power N minus 2, so on and so forth. A to the first, X to the first. If we have any general polynomial, then the limit of that polynomial as X approaches C would equal what? A to the power N, C to the power N, A to the power N minus 1, C N minus 1, and so on and so forth. What happened there? What did this just do? Well, first thing you do, first step, always plug in your value C. That's all we did. Which this equals P of C. And if you have a polynomial, it's not going to violate any rules, because what's the domain of a polynomial? All real numbers, negative infinity, positive infinity. Yeah, so no matter what you put in there, it's going to work. Theorem 3. Limits of rational functions. If P of X and Q of X are polynomial functions, and Q of X does not equal 0, then the limit as X approaches C of P of X over Q of X is equal to P of C over Q of C. Because remember, when we do limits, we take the top and bottom separately. Since they're both polynomial functions, the domain is negative infinity, positive infinity, so everything's going to work. So it's not going to be undefined. We just have to make sure that the denominator is not 0. Pretty straightforward so far? Let's look at some examples. For the most part, it is. The hard part comes when we start having to show proof that it's true. That's going to take us the most time. Example 6. The limit as X approaches negative 1 of X to the third plus 4x squared minus 3 over x squared plus 5. So what would you do here first?
Should I separate them?
You could, but is there something faster we can do?
Plug in?
Plug it in. The first thing we're going to do is plug in -1. And then work it out. So -1 cubed is -1 plus 4. -1 squared is 1 minus 3. -1 squared is 1 plus 5. So we have -4 plus 4 over 6, which is 0 over 6, which makes it what? Not undefined? Good. Yes. Let's see if you waffle on the answer. Zero is a possible answer. It's in the domain. I know a lot of students said, oh, you can't have a 0. Sure you can. It's an answer. Let's see here. Oh. So again, the procedure here, first plug it in there. If it works, it works. The only times you ever have to worry about it is if I'll show you in this next one. Example 7. The limit as x approaches 1 of x squared plus x minus 2 over x squared minus x. First step, first line of attack would be what? Plug it in there. So we have 1 squared plus 1 minus 2, 1 squared minus 1. 1 plus 1 minus 2, 1 minus 1, 0 over 0. Now we got to do something. The first thing we always want to do, either in algebra, is whenever you have polynomials, always do what first? Factor them first. So we have the limit as x approaches 1 of x squared plus x minus 2, x squared minus x. This becomes the limit as x approaches 1. What does the bottom factor add into? Right. You factor out an x. On the top, we have a binomial, so we could try to factor it this way. We have x and x. Since the second sign's a minus, what does that tell us about the signs? They have to be opposite signs. And the bigger number will get the positive sign. So what times what is 2? When you subtract them, you get 1. 1 and 2. So the 2 goes here, the 1 goes there. the x minus ones cancel. The limit as x approaches 1 of x plus 2 over x. Plug those in. 1 plus 2 over 1. So the answer is 3. Well, it's assigned because whenever you have 0 over 0 in a rational expression, that means automatically that they both have something in common. They both have something in common when x equals 1. So what this thing says, when x equals 1, they get 0, 0, which tells us that x minus 1 has to be a 0. So that has to be one of the factors. Again, all these rules from algebra, that's going to come back and haunt you. But yeah, so it tells us, if it wasn't 0 over 0, then it wouldn't tell me anything. It would just be what it is. But that's the clue we're looking. That's what we're hoping for. Because also, what if this instead of 1, what if it was 2? Well, plug it in there. You get 2 squared is 4, plus 2 is 6, minus 2 is 4. 4 minus 2 is 2, so 4 over 2, you get 2. It's just the only thing we look for is when we pick a value for C, we look at when would that cause a problem? Well, looking at the factor of those, the only problem we see is when we have x minus 1 equals 0, which means x equals 1. That's the value our C we're looking at. Okay, let's look at another example. Another example. Example 8. The limit as x approaches 0 of the radical x squared plus 100 minus 10 over x squared. Again, the first thing you would do is plug in 0. So we have 0 squared plus 100 minus 10 over 0 squared. 0 squared is 0, so we have a square root of 100 minus 10 over 0. Square root of 100 is 10. In algebra, again, algebra is the guiding force of calculus. In algebra, when we looked at factoring polynomials or solving large order polynomials, we know that depending on the size of the polynomial, the answers are either going to be positive, negative, 0, or it could be a imaginary or a radical. Those are the only 5 possible answers you can get. If the answers are imaginary or radicals, they always have to come in conjugate pairs. What does conjugate pair mean? What is a conjugate pair? radicals and complex numbers always come in conjugate pairs. What do I mean by complex number? One of those nice writing. What's a complex number? Are you asking me or are you telling me? Right. A complex number is in that form. Every number is written in complex number form. Three plus 5i. Is that complex? Yes. Is that complex? The answer is yes, it is. You have the real part, and then you have the imaginary. So the real part is what in this case? It's 0. And this one's 3. But in this example, 2i, the real part is 0. Is 2 a complex number? Yes. The complex part is 0. Every number can be written as a complex number. Remember, it's a plus bi. The domain for a is from negative infinity to positive infinity for a and b. They can be positive, they can be negative, they can be 0. So every number can be written as a complex number. Now, so we got that defined. What is a conjugate pair? Because remember, you're in algebra, we had 2 sets of rules. One, can you leave your answer like that? No. How do you fix it? By what? Multiply top and bottom by the radical 5. So you get 3 radical 5 over 5. Now things got complicated because now what if we had an equation on the bottom? This is the same thing. This is a complex number. It follows the same rules. We cannot have a radical on the bottom. So how do we get rid of it?
Multiplied by 2 minus the root of 5
Yes.
on both.
You would multiply the top and bottom by 2 minus radical 5.
And then we want a difference squared on 1.
Yes. Because here we have 3 times 2 is 6 minus 3 radical 5. That's on top. Just multiply those. But look what happens on the bottom. 2 times 2 is 4. 2 negative radical 5, so it's negative 2 radical 5. Positive 2 radical 5. Positive times negative is negative. Radical 5 squared. So the radicals disappear. The square root and the square cancel. So our answer on the bottom, it's no more radicals. So this is what is called our conjugate. The conjugate simply changes the sign in front of the radical or the I or the imaginary part. It would work the same way if we had 3 over 2 plus 5i. What do we have to multiply by here? Let me do the next page. Yeah, so we had 3 over 2 plus 5i. So our conjugate would be 2 minus 5i. So on top we distribute, so 6 minus 15i. On the bottom, 4 minus 10i plus 10i minus 25i squared. The middle terms cancel, which is why we have a difference of 2 squares. 6 minus 15i. The I squared becomes what? Because remember, what is I defined as? What makes them? Yes, it doesn't matter. But what defines it as a number? Square root of 1 is 1. It wouldn't be imaginary. It's pretty solid. -1. In engineering, they invented I because they were getting that way. They were getting, everything was working great, but we had a radical that was negative. For example, the quadratic formula. There are some times where when you don't have any solutions, if there aren't any real solutions, they're what kind of solutions? They're imaginary because inside the radical, it's negative. So that's where we get negative. So when you have I equals square root of -1, if I square both sides, the radical and the square disappear, we're just left with -1. Basically, all it does, it changes the sign of the coefficient in front of it. So we have 6 minus 15i over 29. So I needed to discuss that to go back to our question. We got 0 over 0. So how do we fix this equation? We can't factor it. What would you factor?
Will we multiply the top by itself plus 10?
What's that called?
The constant
Yeah. So we have to multiply this whole equation by the conjugate of the numerator. Because what's causing the problems? The radical up here. So we have to get rid of this radical up here. So in our example, we have the limit. The square root of x squared plus 100 minus 10 over x squared as x approaches 0. We know it equals 0 over 0. So what do we have to do to this equation? Is we have to multiply by its conjugate. Can you have a conjugate of x squared? No. The only thing you have a conjugate of is the radical. Since that's minus, we need a plus. So whenever you have radicals in it and you get 0 over 0, always look at conjugates. So we have the limit as x approaches 0. On the bottom, leave it alone since there's not much we can do with it. Let's look what happens on top. So we FOIL it on top. Radical times radical, it just gives us x squared plus 100. This positive 10, this negative 10, they cancel. So we have plus 10 radical x squared plus 100 minus 10 radical x squared plus 100. Negative times positive is negative. 10 times 10 is 100. Simplify. So the middle terms cancel. What else cancels? The hundreds. So on top, all we have left is x squared. On the bottom, we have x squared times radical x squared plus 100 plus 10. X squares cancel. So we have the limit as x approaches 0 of 1 over x squared plus 100 plus 10. We can't simplify anything further, so we just plug it in there. 1 over 0 plus 100 square root plus 10. So 0 plus 100 is 100. So we have a square root of 100 plus 10. Square root of 100 is 10. And there's my answer. I know. It looked easy at the beginning. And trust me, there's also, we're going to talk about a shorter, a faster way of doing it later on. Any questions so far? No, we're only looking at the extreme cases, because a lot of times, like in the homework assignments, you'll get to regular ones, you always just plug it in there first. If it gives you an answer, it's an answer. If it gives you 0 over 0, then you have to see what you have. Again, this goes back to the rules of algebra. The only thing we could done is, since the denominator is x squared, there's nothing we can do with the denominator. So we look at the numerator. It's a radical. So radicals have to come in conjugate pairs. So if we multiply it by its conjugate, it'll give us an answer. It'll help us factor it out, get rid of it. There will be times where we're faced with functions that we can't take the limit of, that we won't be able to figure it out. So what we have to do there is, let's pretend some function f of x, we don't know what the limit is. We can't figure it out. Unknown. So in other words, since we don't know what it is, the limit of it is, so what we can do is this. There's a theorem called the sandwich theorem, and let me give it to you correctly here. But basically what it's doing here, what does a sandwich look like? You have a piece of bread on the bottom, a piece of bread on top, and the stuff in the middle. McDonald's hamburgers, do you know what that meat's made of? What this thing tells us is this, is if this is our unknown function. No, that's not good. And we know there's some value there. This is our f of x. We don't know what that one is at our value c. We don't know what the limit is. But we do have two functions, g of x and h of x. One's above it, one's below it. But they both have the same limit. G of x and h of x at c have the same limit. So you see why it's called sandwich now? Now, so if the f of x has that same point between g of x and h of x, what do you think the limit is of f of x at c? So it has to be L. So that's what the sandwich theorem is. And that's the hardest part, is figuring out a function that works on both sides. That's the hardest part. And here's the theorem. Suppose g of x is less than equal to f of x is less than equal to h of x for all x's in some open interval. Containing C. In mathematics, we would put C is an element of that open interval. So we know g of x is less than f of x is less than h of x for all the x values in this interval. And in this interval, there's a value C also in there. Then suppose that the limit of g of x is equal to the limit of h of x, and they both equal L as x approach the same value C in both of them. Because we know that g of x is less than f of x less than h of x, less than or equal to. Here's the important part. Only look at the endpoints. If g of x and h of x at C both have the same value, what has to happen to f of x? If g of x is less than f of x is less than h of x, and at C, and this is still true. So if g of c is less than f of c is less than equal to h of c, and g of c and h of c are equal, what does that tell us? F of c has to be the same value. So if this equals L and this equals L, then this one has to equal L. So that's what it tells us. then the limit as x approaches c of f of x also has to equal L. That's what the limit tells us. Sounds easy enough, doesn't it? But the problem is figuring out what equations do you use on both sides.
Do you do an example?
Yes, we'll do a couple. Given this, x squared over 4 is less than u of x is less than equal to 1 plus x squared over 2. This is for all x's not equal to 0. Find the limit as x approaches 0 of u of x. So x equals 0 is the point of contention. We're looking for what is u of 0. So what do you think we do first? Plug in 0. So if we have 1 minus 0 squared over 4 is less than u of x is less than equal to 1 plus 0 squared over 2. That equals 0. That equals 0. So 1 is less than equal to u of x is less than equal to 1. So the limit of u of x as x approaches 0 has to equal what? 1. Because of the sandwich theorem. That's how it works. Let's look at another example. Note, the equations you use for g of x and h of x do not have to be complex ones. They could be simple like the one we just did. 1 plus x, 1 minus x. Use the sandwich theorems to help prove this. The limit of theta goes to 0. I'll use x of sine of x. So how do we prove this? Using the sandwich theorem. What does the sine function look like to begin with? So we have pi over 2 pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2. That's all I need. So at 0, what sign? Pi over 2. Negative pi over 2. At pi. Negative pi. At 3 pi over 2. Negative 1. At negative 3 pi over 2 is 1. So the graph looks something like that. We're looking for the limit according to this. We're looking at creating a sandwich theorem at that point there as x approaches 0. So we have f of x. So we're looking for values for g of x and h of x that are below and above our function or this graph. Which ones would you use? What equation would you use? But remember, we're trying to find a sandwich theorem. So g of x has to approach 0 when x goes to 0. And this one has, the h of x has to do the same thing. They both of these have to have the same limit as x approaches 0. One's got to be, but for everything else, this one's got to be smaller than that. This one's got to be larger than that. So what's the formulas? What's that? Negative pi pi? But that's a constant. It's got to be throughout the entire domain. Good try though, but no, it's got to be over the entire domain. The easiest thing is let's look at the value x itself. If we look at the value of x, this one's sine. If we just looked at x, so at 0, it's 0. What is pi over, pi is what? 3 point something. 3 point something divided by 2. Is that greater than 1 or less than 1? It's greater than, so it's up here somewhere. We need to have an absolute value because here it's got to be above there. So we're looking at that function, the absolute value of x. Same thing down here. But we want it to be negative because we want it to be down like this. So these two, one's bigger than it at all times, one's less than it at all times. But since sine is between them at all points x, for every x values, the sine function is lower than h of x, but greater than g of x. It satisfies our condition. What happens as x approaches 0? What does this become? as x approaches zero, what's the negative absolute value of zero? What's the absolute value of zero? So the sign of x as x approaches zero, so the limit as x approaches zero of sine of x would have to equal zero. That's how you structure it. Again, you don't have to go thinking straight too far out of the box. It has to be just a basic equation where it's always true. But they both have to have the same limit at that same value when it comes in the middle. What time we got today? We have about 40 minutes left.
Okay.
We've got 20 minutes left. That's it for that section. That's it for this section. But now I'm deliberating whether we move on to the